operation. I'm here on behalf of our team at STU Center for Large Structure Production, and this is actually a European Commission funded project called Robot Ami. There's a lot to say about the motivation and background of this research, but I will jump right into technical stuff, and you're welcome to check the project's website for more information. Here we have the shotcrete conceptual model that we tried to simulate. Here we have the nozzle that is spraying the material onto the target surface, and there's adhesion, which is the spray is affected by gravity, even in short distances. And also, the spraying more often than not happens when there is an intertwined web of rebars in front of it, which we call obstacle here. In our methodology, we first hypothesized that shotcrete constituents are actually particles. And then we select this swarm of particles and initialize them at the tip of the nozzle with a randomized direction and velocity bounded by this spray cone. And this spread parameter is actually tunable in our simulation with, if needed. One difference of our approach to previous research is that as soon as the particle is emitted, it's affected by gravity, and at each time step, a velocity in the z direction or in downwards direction is added to the particle. So instead of hitting that xyz coordinate, it would hit xyz prime. Then there's this lifespan of every particle. If it adheres to a surface, becomes deactivated, or if it goes down than the zero level, it would also get deactivated. We assume that at small time steps, particles travel on lines. Therefore, finding the collision problem is conveniently reduced to finding collision between a line segment and, for example, a plane that represents a wall, or other simple geometries such as cylinders. Therefore, at the point of contact, we know the position at the moment and the next position. If there is a collision, we know the point. We could calculate the point of contact. And at the point of contact, the particle is assigned a random variable, which we call chance. Also, consulting what is known in the literature as Melby curves, which he did some experimental work on the how the rebound is affected, what parameters are affecting the rebound phenomenon. And therefore, we can conclude that if the particle rebounds or sticks to the wall. If it rebounds, then a new velocity is assigned to it, which is the reflection with respect to the normal at that point, and then also the coefficient of restitution. But if it sticks to the wall, then it becomes deactivated, and then the height field and the visualization is updated. Here again, we have this robot TCP here, which has the position and orientations of the robot. Then we can put different tools, but here we need a shotcrete nozzle, and then the emitter with all of its parameters. Then when the particles are emitted, they either rebound or adhere to a surface at the point of collision. We also have this different types of obstacles, flat finite planes or finite cylinders. We also have this cohesion model, which detects cohesion failure, and then if cohesion happens, then updates the height field. Here's the output of our simulation. We focused on kind of data structure that is suitable for machines and robots. Therefore, here we have the 2D grid that has the values. As soon as the particle adheres to any point on the surface, then we update that value with one integer, for example. But also, it's very nice to have a representation of this in our simulation in the form of this heat map, which is basically a mapping between a value and a color. Now we can see an animation of what we have at the moment. Here we have the construction side and then the robot, which is a conceptual robot and with different modes of motion that goes into the scene. And here we can put like planes, different planes that we can capture the accumulation of concrete on them. And also on the ground to capture the rebound. And if the simulations are accurate enough, even the robot knows where the rebound would land, and it can avoid the rebound to protect itself, or to protect the mobile platform, which becomes really slippery if it goes into the concrete. And here we can see that with 10 million particles and 100,000 being emitted every second, we have almost real-time performance. We presented a new realistic shotcrete process simulation, which is based on a particle system. There are certain advantages with the previous work. Can more efficiently incorporate gravity and other dynamic forces such as air drag. And it can simulate interaction with obstacles. The output is machine readable. And also, for next steps, we are trying to improve the model's fidelity and do verification and validation. Ultimately, design a digital twin. Hey, my name is Reza, and at the center, STU Center for Large Structure Production, we focus on bringing digital and robot solutions to sectors construction, maritime, and energy. Therefore, please visit our website. That's it on my side. Thank you very much.